After studying this module, you shall be able to know about the term functional form. You shall also learn how to use functional forms in different models. We shall also be able to identify the interpretation of coefficients and their significance. You will also learn to evaluate the model which best suits to given problem. In the end, we would try to analyze whether the outcomes are consistent with real life situations. Introduction. So let me introduce the concept of functional form to you. Through the use of multiplicative terms in interaction models, we can assess how slopes vary conditional on the value of some other covariate. In this sense, we can estimate more sophisticated linear relationships among our variables. However, one thing that we haven't considered to this point is how to incorporate non-linear relationships inside of a linear regression model. Why might we want to think about doing this? The reasons are simple. First, given the desirable properties of the OLS model, it would be nice to use our data and stay within the framework of the linear model. Second, if a relationship is nonlinear, then transformation on X may produce a better fitting regression model than one where the relationship between X and Y is constant and linear. So despite its name, the classical linear regression model is not limited to a linear relationship between the dependent and the independent variables. In this module, therefore, we are concerned primarily with models that are linear in the parameters, which they may or may not be linear in the variables. Theory of functional forms. Consider a vector xi consisting of xi1, xi2, xik of k variables for each observation I. The L functions f1 into xi, f2 of xi, fl xi map the k-dimensional vector xi into L scalars z1i, zi2, zil. The function gyi is a univariate function of the dependent variable. The nonlinear econometric model zy is equal to beta 0 plus beta 1 f1 xi plus beta 2 f2 xi so on up to beta l fl xi plus ui. This can therefore be written as zy is equal to beta 0 plus beta 1 z1 zi1 plus beta 2 zi2 so on up to beta l zil plus ui. The latter is the usual multiple regression model with L plus 1 regressors as long as all necessary assumptions about the error term and the transformed independent variables zi equal to 1, zi1, zi2, zil are satisfied. All properties of OLS are therefore preserved. The use of vector approach is to show that we could extend the one equation analysis to many equations in n-dimensional space and can find the solutions to the beta coefficients. Coming back to the one regression equation model, we consider below some of the other functional forms. In the sections that follow, we consider some commonly used regression models that may be nonlinear in the variables but are linear in the parameters, or that can be made so by suitable transformations of the variables. In particular, we discuss the following regression models: the log linear model, second, the semi-log models, third, the reciprocal models, and fourth, the logarithmic reciprocal model. Consider the following model known as the exponential regression model. yi is equal to beta 1 xi raised to power beta 2 into e raised to power mu I or ui, which may be expressed alternatively as ln yi is equal to alpha plus beta 2 ln xi plus ui, where alpha is equal to ln beta 1. Ln is nothing but natural log, which is nothing but log to the base e, and e is equal to 2.718. We can write this model as linear in the parameters alpha and beta 2, linear in the logarithmic or logarithms of the variables y and x, and can be estimated by OLS regression. Because of this linearity, these models are called log-log, double-log, or log-linear models. If the assumptions of the classical linear regression model are fulfilled, the parameters can be estimated by the OLS method by letting the assumptions go fulfilled. You can see this in your diagrams where we have the diagram for linear estimation, a straight line, and the diagram for or the curve for the exponential distribution. We can write down yi star equal to alpha plus beta to xi star plus ui, where yi star is ln yi and xi star is equal to ln xi. We have different diagrams for different values of beta 1 and beta 2, which I'm sure you can observe from the slides. The OLS estimators alpha hat and beta 2 hat obtained will be best linear unbiased estimators of alpha and beta respectively. The slope coefficient of the log-log model beta 2 measures the elasticity of y with respect to x, that is the percentage change in y for a given or a small percentage change in x. Thus, if y represents the quantity of a commodity demanded and x its unit price, beta 2 measures the price elasticity of demand, a parameter of considerable economic interest. Two special features of the log linear model are: the model assumes that the elasticity coefficient between y and x, that is beta 2, remains constant throughout. Another feature of the model is that although alpha hat and beta 2 hat are unbiased estimates of alpha and beta 2, beta 1, the parameter entering the original model, when estimated as beta 1 hat equal to anti-log of alpha hat, is itself a biased estimator. The Log-Lin Model. This model is like any other linear regression model in that the parameters beta 1 and beta 2 are linear. The only difference is that the regressant is the logarithm of y and the regressor is time, which will take values of 1, 2, 3, etc. Models like these are called semi-log models because only one variable, in this case the regressant, appears in the logarithm form. A model in which the regressant is logarithmic will be called a Log-Lin model. Let us examine the properties proportional or relative change in y for a given absolute change in the value of the regressor, in this case the variable t. That is, yt is equal to y0 into 1 plus r raised to the power t. Now this can be written as ln yt equal to ln y0 plus t ln 1 plus r. Now let beta 1 is equal to ln y0 and beta 2 is equal to ln 1 plus r. In that case, we can write this equation equal to ln yt is equal to beta 1 plus beta 2t plus ut. Beta 2 is equal to relative change in regressant upon absolute change in regressor. If we multiply the relative change in y by 100, it will then give the percentage change or the growth rate in y for an absolute change in x, the regressor. That is, 100 times beta 2 gives the growth rate in y. 100 times beta 2 is known in the literature as the semi-elasticity of y with respect to x. Instantaneous versus compound rate of growth. The coefficient of trend variable in the growth model beta 2 gives the instantaneous, which means at a point in time, rate of growth, and not the compound, or which is over a period of time, rate of growth. But the latter can be easily found from by taking the antilog of estimated beta 2 and subtracting 1 from it and multiplying the difference by 100. For illustrative example, suppose the estimated slope coefficient is 0.00743. Therefore, antilog of 0.00743 minus 1 is equal to 0.00746 or 0.746%. Thus, in the illustrative example, the compound rate of growth was about 0.746% per quarter, which is slightly higher than the instantaneous growth rate of 0.743%. This is, of course, due to the compounding effect. Lin-log model. Instead of estimating model, researchers sometimes estimate the following model, which is yt is equal to beta 1 plus beta 2t plus ut. That is, instead of regressing the log of y on time, they regress y on time, where y is the regressant under consideration. Such a model is called a linear trend model, and the time variable t is known as the trend variable. If the slope coefficient in it is positive, there is an upward trend in y, whereas if it is negative, there is a downward trend in y. Unlike the growth model just discussed, in which we were interested in finding the percent growth in y for an absolute change in x. Suppose we now want to find the absolute change in y for a percentage change in x. A model that can accomplish this purpose can be written as yi is equal to beta 1 plus beta 2 ln xi plus ui. For descriptive purposes, we call such a model as a Lin-log model. Let us interpret the slope coefficient beta 2 in this case. As usual, beta 2 now is equal to change in y upon change in ln x. This is equal to change in y upon relative change in x. If x changes by 0.01 unit or 1%, the absolute change in y is 0.01, which is beta 2. If in an application one finds that beta 2 is equal to 500, the absolute change in y is 0.01 into 500 is equal to 5. Therefore, when regression is estimated by OLS, do not forget to multiply the value of the estimated slope coefficient by 0.01, or what amounts to be the same thing, divided by 100. If you do not keep this in mind, your interpretation in an application will be highly misleading. The practical question is, when is a Lin-log model useful? An interesting application has been found in the so-called angel expenditure. Angel found that food expenditures are an increasing function of income, but that
food budget shares decrease with income, which explains the non-linearity. Goods with income elasticity less than or equal to 1, repeat. Goods with income elasticity which is greater than 1 are known as luxuries, and goods which have income elasticity between 0 and 1 are known as necessity. And Angel found that food is a necessity. Reciprocal model. So far, we have considered models written in linear form, that is y is equal to beta 0 plus beta 1 x plus u. It implies a straight line relationship between y and x. However, sometimes economic theory and observations of data will not suggest that there is a linear relationship between variables. One way to model a non-linear relationship is the equation, which is y is equal to a plus beta upon x plus e, where the line asymptotes to the value a as x increases to infinity. However, y is equal to a plus b upon x plus e is not a linear equation, since it does not trace out a straight line between y and x. And OLS only works, which means it fits a straight line to minimize RSS or residual sum of the squares, if we can somehow make it linear. In the above case, we do this by creating a variable equal to the reciprocal of x, that is 1 by x, so that the relationship between y and 1 by x is linear, that is a straight line. So that y is equal to a plus b upon x plus e becomes now equal to y is equal to a plus b star into 1 by x plus e. And now linear in parameters, which means we can regress y on 1 upon x rather than y on x. The only thing now need to be careful about is how to interpret the coefficients from this specification. Now dy by d 1 upon x is equal to b, or I may say that b is equal to dy upon d1 by x. But dy upon dx therefore now is equal to minus b upon x square, which is linear in parameters, but which isn't and effect not constant. So if you compare dy upon d1 by x equal to b, it is linear in parameters. But if you compare dy by dx, which is equal to minus b upon x square, this is not linear and the effect not constant. Now, models of the following type are known as reciprocal models. Although this model is non-linear in the variable x because it enters inversely or reciprocally, the model is linear in beta 1 and beta 2 and is therefore a linear regression model. Now, this model has these features. As x increases indefinitely, the term beta 2 into 1 upon x approaches 0. Please note that beta 2 is a constant, and y approaches the limiting or asymptotic value beta 1. Therefore, models like this above have built in them an asymptote or limit value that the dependent variable will take when the value of x variable increases indefinitely. Polynomial functional forms express y as a function of the independent variables, some of which are raised to powers other than 1. For example, in a second-degree polynomial, also called a quadratic equation, at least one independent variable is squared. So we can write down yi is equal to beta 0 plus beta 1 x1i plus beta 2 x1i square plus beta 3 x2i plus epsilon I. The slope of y with respect to xi in equation now is that delta y upon delta xi, or x1i, x1 is equal to beta 1 plus twice beta 2 x1. Note that the slope depends on the level of x1 now. Example 1. If you are trying to estimate the amount of time it takes a person to complete a complex physical task as a function of the air temperature, holding humidity constant, you might suspect that time would be minimized at about 70 degrees Fahrenheit and higher when the air is either colder or warmer. The relation should be a U-shaped one. So we might choose to model this as Ti is equal to beta 0 plus beta 1 Fi plus beta 2 Fi square plus epsilon I. You would expect the estimated coefficient on Fi to be negative and the estimated coefficient on Fi square to be positive. This will produce a curve with the desired U shape. We can have another example. Example 2. One part of my dissertation looked at the cost of operating scrubbers on coal-burning power plants. The dependent variable was the annual operating and maintenance cost, yi, and the explanatory variables were such things as the level of efficiency of the scrubbers, ei, the total amount of coal burned, ci, the sulfur content of coal, si, and the percentage of hours during which the scrubber was operated, denoted as pi. If any of these explanatory variables took the value 0, then there would be no scrubbing done and the cost should be 0. Further, if any of these were to double, I would expect that the total cost would rise by some percentage, perhaps doubling. As a result, the model used was yi is equal to a into ei raised to power b into ci raised to power c into si raised to power d into pi raised to power f into epsilon I. Taking the natural log of each side allowed us to estimate ln yi equal to ln a plus b ln ei plus c ln ci plus d ln si plus f ln pi plus epsilon I. Example 3. In talking about demand relationships, one of the most important considerations is the price elasticity of demand. Among other things, this reveals the effect that a price change will have on revenue. So if we estimate the equation Qt is equal to beta 0 plus beta 1 pt plus epsilon t, we get the slope of the demand curve, which isn't terribly interesting. However, if we estimate Qt is equal to A into Pt raised to power beta plus epsilon t, the coefficient of beta is the price elasticity of demand. Ln Qt then is equal to ln A plus beta ln Pt plus ln epsilon t, or ln Qt is equal to beta 0 plus beta 1 ln Pt plus epsilon t prime. The estimate of beta 1 is the estimate of price elasticity of demand. To be more clear about doing this, if you have data on prices and quantities at different points in time, all you need to do is generate new variables equal to the log of the price and the log of the quantity, and do a linear regression using these new variables. The resulting coefficient on price will be the estimate of elasticity. In general, anytime you estimate a model of this form, the slope coefficients are elasticities. That is, they represent the relationship between a percentage change in the explanatory variable and the resulting explanatory variable in the dependent variable. For example, looking through a catalog for bicycle parts, you would notice that lighter parts carry higher prices. If you regressed ln price on ln weight, you would calculate the weight elasticity. Choice of functional forms. The choice of a particular functional form may be comparatively easy in the two-variable case because we can plot the variables and get some rough idea about the appropriate model. The choice becomes much harder when we consider the multiple regression model involving more than one regressor. Some guidelines are offered. First, the underlying theory. For example, the Phillips curve may suggest a particular functional form. Second guideline is it is good practice to find out the rate of change, that is the slope of the regressant with respect to the regressor, as well as to find out the elasticity of the regressant with respect to the regressor. If we want to compare goodness of fit of models in which the dependent variable is in logs or levels, then we cannot use the R square. The total sum of the squares, or TSS, in Y is not the same as TSS in ln Y, which means the summation of yi minus y bar square, summation of I over 1 to capital N is not exactly same as the summation of ln yi minus ln y bar square, where I is again from 1 to capital N. So comparing R square is not valid. Instead, the basic idea behind testing for the appropriate functional form of the dependent variable is to transform the data so as to make the RSS comparable.
So students, let us summarize what we have learned in this module. We have learned that a functional form refers to the algebraic form of a relationship between a dependent variable and regressors, or also known as explanatory variables. We have seen that the simplest functional form is the linear functional form, where the relationship between the dependent variable and an independent variable is graphically represented by a straight line. The interpretation of coefficients is different in alternative functional forms. In the following formulations, y represents the dependent variable, x the independent variable, and a is the y-intercept. B is the slope coefficient. ln y and ln x represent the natural logarithm of y and x respectively, and e is an error term. The first functional form we have learned is linear, where we have mentioned that y is equal to a plus bx plus e. In this functional form, b represents the change in y, which is in units of y, that will occur as x changes by 1 unit. The second form we have learned is semi-log form, in which we have expressed ln y equal to a plus bx plus e. In this functional form, we have learned that b is interpreted as follows. It gives us 1 unit change in x will cause a 100% change in y. For example, if the estimated coefficient is 0.05, that means that a 1 unit increase in x will generate a 5% increase in y. The third form we have learned is double log, where we have expressed ln y is equal to a plus b ln x plus e. In this functional form, b is the elasticity coefficient. It means a 1% change in x will cause a b% change in y. For example, if the estimated coefficient is -2, that means a 1% increase in x will generate a -2% decrease in y. Sometimes you would know a regression model may not contain an explicit intercept term known as regression through the origin. In such models, the sum of the residuals of ui is non-zero, and the conventionally computed R square may not be meaningful. So unless there is a strong theoretical reason, it is better to introduce the intercept in the model explicitly. The units and the scale in which the regressant and the regressor or regressors are expressed are very important, because the interpretation of regression coefficients is critically depend on them. I'm sure you would appreciate that concept. In the log linear model, both the regressant and the regressors are expressed in the logarithmic form or logarithmatic form. Models like reciprocal models have built in them an asymptote or limit value that the dependent variable will take when the value of the x variable increases indefinitely.